So, hi everybody. The title of this paper is a multi-objective optimization platform for artificial lighting system in commercial greenhouses. And I'm Jing. So this presentation is divided into these 5 parts. First is the background. Just as Daniel just mentioned, this is the overview of the project, and this paper focuses on the work package 3, that is the climate compartments. One of the tasks of this work package is to optimize the climate uh, of individual greenhouse compartments to save energy and reduce the production cost, but without compromising the production quality. Um, Not like today. I think if you live in Denmark or familiar with the weather in Nordic countries like Denmark, you must be very familiar with such weather. The keywords for the weather, especially in the winter, are always dark, cold, rainy, vitamin D, and so on. So this causes an issue that is insufficient photosynthetically active radiation, and we call it PAR in this presentation. This PAR is the efficient part in light for the photosynthesis of plants, so it's critical for the growth of plants. In greenhouse system, we can use artificial lighting as a supplemental source for such light. But this also introduces another issue that the electricity cost of artificial lights accounts for a large percentage of the overall cost of plant production. To solve this problem, our center develops a multi-objective platform called Journalite to solve the artificial lighting optimization problem. So this is the demonstration of the artificial lighting system in greenhouses. First, the local sensors collect the data inside and outside of the greenhouse. Besides, there are some other external data like weather forecasts and electricity prices. All of these data are collected by the database. And in Journalite, we abstract the multi-objective problem of artificial lighting in greenhouses as an objective model. And based on this model, Journalite uses genetic algorithm and uses the relative data from the database. Finally, it outputs an optimal light plan of the future 72 hours to the hardware controller, and it is converted to a drive signal to finally control the light switch. So this is the overview of this system. But until now, there's no analysis talking about the consequences of Journalite on the coverage of Pareto Frontier or the final light plan selection mechanism from the Pareto Frontier. So in this paper, a new um, alternative version of Journalite, we call it Journalite Ind, is introduced. And so there are 2 versions of Journalite. The old version, we call it Journalite in this presentation, and the new version as the Journalite Int. And the IND is short for independent. So the purpose of this paper is to analyze the impact of the previous genetic algorithm strategy on these 2 aspects. And by comparing the advantages and disadvantages of these 2 versions, this paper also contributes to some implementation suggestions about the genetic efficiency and computation speed in general areas. And the artificial lighting optimization problem can be abstracted as 7 objectives. And all of these objectives are described as evaluation functions like this equation. And And all of these evaluation functions can evaluate a suggestion for a light plan by returning a cost. And the target of such objectives is to minimize the cost of individual objectives. So in this equation, this F represents the evaluation functions, and the subscript Fm is the index of the objectives. And this X is the vector of light plan. So the size of it is 72, represents the 72 hours. These are the 7 objectives that is the abstract model of the artificial lighting problem in Journalite. And these objectives cover different aspects of the problem, such as the plant growth, that is the production quality, and the physical equipment protection, and also include to reduce the electricity cost and save energy. But for the global um, goal, goal of this project, that is to ensure the production quality, but minimize the electricity cost and save energy. The relative importance of these objectives are different. So in the two versions, they use different methods to describe such relevant importance relations. In the old version, it uses a concept of priority to describe that the smaller the real number is, the higher priority the objectives have. And the objectives with the same number have the same priority. In the new version, it uses a directed graph, and we call it a relative importance graph to describe such relation. And the objectives in the same vertex have the same relative importance. And the arrows come from the vertex that have relative more importance and points to the the vertex that have relative less importance. And this figure is the flow chart of the optimization process in different steps. The two versions have different implementation strategies. And this table is a summary of the comparison of these difference of the two versions. And the color corresponds to different steps. And for the aspect of genetic algorithm implementation, we can see that there are 3 differences, and all of these differences can influence the efficiency of evolution and computation. For example, the first difference is about the Pareto Frontier update strategy, and the second difference is the comparator that is used for checking the dominance of a child solution. And the third difference is about the computation efficiency. And in the new version of Journalite, it uses a post-normalization method to normalize the cost scale of different objectives to be between 0 and 1. That's because the cost scales of different objectives may be quite different with each other. So they can cause an issue that the objectives that have the same priority or in the same vertex, but they have different weights that caused by the different cost scales. But if the objectives in the same vertex or have the same priority, they should have the same weight. So in the new version, this issue is solved by the post-normalization But in the old version, it doesn't have any process of such issue. And the next difference is about the relative importance relation description, and we just talk about it. Then it comes to the social welfare matrix. This is a concept that is borrowed from the economics area. So the social welfare matrix can provide a metric to score solutions for selecting the final light plan from the Pareto Frontier. And in the old version, it has only one solution, social welfare matrix, and that is utilitarian. But in the new version, it has multiple such metrics, so it's more flexible. Then we have some experiments to compare the difference, to compare the influence of the difference between the two versions of Journalite. And these are the experimental configurations. To compare them, so they have the same experimental configuration for the two versions. The point I'd like to say is first is the fixed light hours. So this is the vector of the fixed light hours in 24 hours. All of these zeros represent in these hours, the artificial light must be switched off. And this is mandatory. And another point is there are two PAR goals are involved in these simulations. They are 10 and 4. The reasons for these two PAR goals are that when the PAR goal is 10, that means it's impossible to have any solutions that they can fulfill the fixed light hours can also fulfill the PAR goal. But when the PR goal is 4, it's possible to have some solutions to fulfill both of these objectives. And there are 3 simulation dates. And for each simulation situation, 3 runs are executed on the 2 versions respectively. This is the simulation results on January 10 to 12 in 2020. In these figures, we can see the gray areas represent the fixed light hours. That means in these hours, the artificial light must be switched off. And the blue curves is the electricity prices. And the green curves are the natural PAR value. And these step curves represent the final light plan from these 2 versions of Journalite. The solid steps represent from the new version, and the dot curves are from the old version. And the high step is switch on, and the low step is switch off. And this is the simulation results on November from 1st to 3rd in 2020. From this result, we can see that there are several dot curves are involved. That means in these 3 rounds, the light plan across these 3 rounds in the old version are different. So so all of these solutions, all of these light plans are drawn here. And this is the simulation results on December 20 to 22. This table is the summary of the comparison of all of the simulation results. These are the 2 PAR goal, and these are the simulation time. These columns are the sizes of Pareto Frontier of the 2 versions. For the old version, we can see that for some situations, the the sizes of the Pareto Frontier across the 3 rounds are quite different. So I listed all of them here. But in this situation on November 1st, when the PAR goal is 4, the sizes of Pareto Frontier across the 3 rounds are the same. But the issue is the solutions in these Pareto frontiers are different. So they are also listed here. And then we compared the Pareto frontiers from the old version with the new version. And there are 3 possibilities about the comparison results. That maybe some of the solutions from the old version have been covered by the new version's Pareto Frontier, or they are not non-dominated or dominated by the new version. So we can see when the PAR goal is 10, part of the solutions from the old version have been covered by the new version's Pareto Frontier, and part of them are dominated. But when the PAR goal is 4, all of the solutions from the old version are dominated by the new version. And what we can notice, what we need to be noticed is that there's no non-dominated solutions from the old version. So from analyzing this table, we can say that for the old version, the genetic algorithm implementation strategy can cause the Pareto frontier to be incomplete. That means there are some non-dominated solutions are missing. So for the new version, the genetic algorithm implementation can cover a much broad and more complete Pareto frontier. So that means the quality of the Pareto set in the new version is intact or improved compared with the old version. And from analyzing the simulation results, and here is an example of the results, we can see that for the new version, the light plan can always select the hours that are with relatively lower electricity prices and avoid higher electricity prices. And another point is about the average time consumption for the 2 versions. For the new version, it's the evolution generation and the simulation time for evolution generation for the new version is approximately 5.6 times faster than the old version. In conclusion of this paper, although there are some previous works talking about some specific implementation points of Journalite, this paper explains the entire implementation process of the 2 versions. Besides, this paper also contributes to some implementation suggestions about genetic algorithm efficiency and computation speed in general areas. Besides, there are also some future works to do for this paper. For example, the time-saving problem for the optimization process, and this can be improved from increasing the computation efficiency or increasing the computation ability of the hardware. Another thing that we can do in the future is to do some practical experiments. So that's all from me. Thanks for your attention.